So our next standard is being able to identify properties of functions. Okay. Last week we talked about the shapes of different functions, but now we're going to get into more even the properties about them. Specifically, this standard is going to focus on domain range, vertical asymptotes. That's what the VA is going to be, vertical asymptotes, or holes. We'll talk about that a little bit. And we'll talk about continuity as well. These are kind of the things that are going to fall into this standard. All right?
Yeah.
So, the first one, that function that I want to start with, is y equals 5 over x minus 2. Of the 10 parent functions that we studied last time, which one is this a family member of?
Rational.
Rational? And what's that function look like? Yeah, you're right. It's rational.
Y equals 1 over x.
Very good. Yep. This would be a member of the rational family, or you guys might remember it as y equals 1 over x, right? Why'd you say that, Lenny? You're right. Why'd you say that?
It's a fraction
Because it's a fraction, and specifically, where's the variable?
on the bottom.
On the bottom. Okay? If the variable is on top, I wouldn't call it a rational function. If it was x over 5, that'd actually be a linear function. It'd be like 1/5 x, okay? So, with the variable in your denominator, we're looking at a rational function. You can have variables both, but anytime there's definitely a variable in your denominator, you're looking at a rational function. Okay? Alright, good. So, let's talk about domain. It's a good place to start, okay? Domain of this function. What do you guys think of when you think of domain? X values? Okay. Give me a little more. What about X values?
Ones that are touched by the graph or by the
So if you were to graph this, the X values that the graph touches. Okay? Alright, great. What else?
yeah.
So you're telling me if I want to figure out the domain of this function, I'm going to have to get out a graphing calculator or get out a sheet of graph paper, and I'm going to have to graph it and then tell you what X values that graph touches? What's another way to do it then? If the graph of this touches an X value, that means that for that X value, there's also a Y value that goes with it, right?
Yep.
So like, will this graph touch an X value of 7? Well, yeah, because if I plug in a 7 for X, I'll get a Y value for Y, right? Are there any X values that if I would plug them in for X, I would not get a value for Y?
Two.
2 Y, Colin.
Because 2 minus 2 is 0, and anything over a 0 is undefined.
Yeah, if you plug in a 2 here, 2 minus 2 is 0, 5 divided by 0, try to do that on your calculator, you're going to get an error message, undefined, right? You can't divide anything by 0. So 2 is definitely not in the domain. Because this graph can never hit an X value of 2 because there's no Y value to go with it. Are there any other numbers that you could not plug in for X? Everything else going to be good? You'll get an answer, you'll get a numerical answer. So would you agree that the domain of this function is every number except 2?
Yeah.
And the reason why, you can't divide by 0, right? Your domain is usually going to be almost every real number. But there are some things in math you can't do. You can't divide by 0. So if there are X values that make a denominator equal to 0, you know that number, that X value, is not in the domain. So my domain is all real numbers except 2. How do I write that? every number from negative infinity to 2, and then every number from 2 to positive infinity. That would be the domain of that function. You're welcome to follow along on a graphing calculator, or not, but I'm going to use my graphing calculator a little bit right here, right now. But I have 5 over x minus 2, is that right?
Yeah.
So I use my graphing calculator to go ahead and graph this quickly here. Take a look at it. Kind of looks like that parent function 1 over x, doesn't it?
Yep.
Okay, just moved a little bit, maybe a little steeper. Okay, we'll talk about those things later on here. So you'll see the graph touches all these all these x values, and then what do you think's going on here at x equals 2?
Nothing.
Correct, it never touches it. So what do you think?
It's getting real close.
It's getting really close to it, and there would be a vertical asymptote at 2. Okay, your graphing calculator will not show that, but what's going on here is there is a vertical asymptote at x equals 2. The graph will get really, really, really close to 2 here, okay, as far as the x values go, and it'll get really close to 2 here, but at 2, the graph never touches it, because if you try to plug in a 2 for x, you get undefined or error for y. Let me go to my table of values. Right above the word graph, it says table. You know, the calculator makes a little table for you. Okay? If you plug in a 0 into this function, you'll get negative 2.5. You plug in a 1, you'll get negative 5. You plug in a 2, you'll get error. You can see right here in your table of values that also this graph is undefined when x equals 2. You can tell from the table of values. You shouldn't need a table of values to tell you that, but you could using that function. Okay? Just an FYI, graphing calculators can be super duper helpful over the next month with what we're going to be doing. Okay? So, if you recall, vertical asymptotes were one of the things that we had in the standard. Okay? Vertical asymptotes. First of all, they are vertical. I'm going to call them imaginary, but I mean, they're not imaginary. They're just, you don't see them, okay? Vertical, kind of imaginary lines. The graph approaches, but never touches. Okay, vertical asymptotes are vertical imaginary lines the graph approaches but never touches. And the way to know where the vertical asymptote will be located, figure out what x value makes the denominator equal 0. Whatever x value makes the denominator, the bottom, equal 0, that is where your vertical asymptote will be. So what x value makes the denominator equal 0? So for this function right here, where's my vertical asymptote?
2.
X equals 2. Okay? Write the x equal 2 part column. Don't just write the number 2. I want you to write x equals 2 so that way it's representing a vertical line. Okay? So my vertical asymptote, x equals 2. Because that is the x value that makes the denominator equal 0. Any x value that makes the denominator equal 0, there will be a vertical asymptote there. Okay? So eventually you're going to be able to look at this function here and say, okay, I know this graph's going to look something like the parent function. And I know it's got a vertical asymptote at 2. So without even graphing it, you're able to tell a few things already. Now the graph helps, for sure. But I want you to be able to look at functions and have an idea of what their graph looks like ahead of time. Okay? Alright, what do we got? What else? We got range. We'll talk about bowls a little bit here, and then we'll talk about continuity. Okay? Range. We know what the range is, right? Range is all of the y values. Okay? To be honest, nearly all of you will use the graph to help you find the range. You probably won't think it out like we did domain. You probably will want to graph it to figure out what the range is. Range is the y values. So in other words, I need to figure out what y values this function will equal. Okay? Well, I know it'll never equal 0. Because 5 divided by something will never equal 0. In fact, and the only way y could be 0 is if this was 0 right here, right?
Yeah.
So this function will never hit a y value of 0. So I know 0 is not in my range. But I think it'll hit any other value. I think it'll hit really big positive numbers. I think it'll hit really low negative numbers. Okay? Like if I make this 2.001. Well, 2.001 minus 2 would be 0.001, and 5 divided by 0.001 would be 5,000. So it hits really big numbers. It's really small numbers. Again, you guys saw the graph of it a second ago. The graph hits really, really big y values. It comes down here, gets really close to 0. It hits negative y values and goes all the way to negative infinity. So it touches every y value except what? 0. It touches every y value except 0. Can you guys tell that from looking at the graph of it here?
Yeah.
Okay? So what am I going to write down for my range? Negative infinity to 0. And 0 to positive infinity. Okay? So range I get off my graph. Okay? So I got domain, I got range, I took care of the vertical asymptotes, we haven't talked about holes yet, we'll get there. And the last one here is continuity. Continuity is all about whether a function is continuous or not. For a function to be continuous, you need to think, we did this a little bit with piecewise, okay? You need to think, could I draw this entire graph with never my pencil leaving the paper? Okay?
No.
So in this case, yeah, good. So I'm going to start way back here at negative infinity. I could draw the graph, draw the graph, draw the graph, draw the graph, and this goes all the way down to negative infinity. In order to draw this part, I'm going to have to pick up my pencil to draw the next part, right? Is this function continuous?
Nope.
No, it's not continuous because you have to lift your pencil off the paper. You can't draw, like the sine curve, that's continuous, right? You can draw that forever if you wanted to. Pencil will never have to come off the paper. the line y equals x. That's continuous, right? Okay? This is not continuous because the pencil comes off the paper. That's not very mathematical, all right? But it makes sense, I think, right? Okay? So this is definitely not a continuous function. It's definitely not continuous. And then because it is not continuous, I want you to tell me what type of discontinuity it has. There are three types of discontinuity. If a graph looks like this, where there's just a hole in the graph, that's called point discontinuity. What's that?
What is that?
I'll show you. I'll show you with. It might not happen today, but I'll definitely have it around. Point discontinuity. That is one type of discontinuity. It's a removable discontinuity. Like I could make this graph continuous. I could make this graph continuous by filling in the hole, right? If I fill in that hole, then it's a nice continuous graph. So that's why it's a removable discontinuity. This is the only type of discontinuity that's removable. I can make this continuous by assigning a y value for that x
So
value.
it's just not assigned.
Okay, correct. Yep.
Okay.
Yep. I'll give you an example of a function that would have that probably tomorrow. Okay. There are two other types of discontinuity: infinite discontinuity and jump discontinuity. These are non-removable. There's no way I could make these functions continuous. It's impossible. You can't connect them because we know the graph can never hit that value. Plus, you'd have to draw a vertical line, and a vertical line is not a function anymore. So you couldn't make that continuous. And to make this one continuous, again, you'd have to fill in the hole and then draw a vertical line. And a vertical line is not a function because there are multiple y values for the same x value. So again, you could not, these types of discontinuity have to stay discontinuous. They cannot become a continuous function. That's why they are non-removable. You cannot remove the discontinuity.
On the jump discontinuity, is that supposed to be two arrows coming from that circle? Or
No,
did you-
that was just a very poorly drawn one.
Oh,
It's
okay.
just one graph.
Okay.
For some reason it just came back. So let's go back to the function that we had. What type of discontinuity was going on? Infinite. How can you tell? There's a vertical asymptote. That's the key. Okay? Anytime you have a vertical asymptote, you're going to be working with infinite discontinuity, and that is definitely non-removable. Okay? So on our functions, not only are you going to write not continuous, or you can write discontinuous. I don't care how you want to do that. Just make sure you write it's not continuous. Okay? It is non-removable, and it has infinite discontinuity. Okay. If you would just write these two things, you probably don't need to write that top one because that's kind of obvious. If you write this, I know you know it's not continuous. if you say it has some sort of discontinuity, then obviously it's like you're saying it's not continuous. So I guess when you are going to describe the continuity of a function, if you would just say this for this one, that would be great. So on this standard, you'll be given a function, and you'll be asked to find the domain, the range, where and whether it has a vertical asymptote or a hole. Which again, I haven't done one that has a hole yet, but that will be coming. And then you'll be asked to describe its continuity. And you could be given any type of function and be asked to explain those things.
Give us a log pool.
You could have any of the 10 type of parent functions, yes.
Okay.
And we're going to practice a lot,
Okay.
okay?
'Cause I don't know how to do a log.
Yep.
Are you gonna have them talk about horizontal?
I'm going to save that for chapter 4. It kind of falls more into that one.